Share screen. And you can do it, iPad. I know you can do it. You're having trust issues? What the hell? All right, let me try this again. Stop, go. Go. Don't make me big, iPad. All right, let me try the old unplug and replug. Let's see if that works. You bastard. Come on. There we go. Hallelujah. Finally. Thank goodness. Well, I was about to have it. No! What? Okay, there it is. Very good. Holy cow. That's what you call panic inducing. But in any case, looks like now we're good to go. All right, so now let's get back to where we were on Monday. So you will recall that what we were doing was trying to relax our assumption of microcanonicality. Okay, so using the word microcanonical indicates that what you're doing is you're looking at fixed energy. So some fixed constant value of the energy. And it goes without saying that we are also looking at fixed constant values of the volume of our system and the number of particles. And so now what we were trying to do on Monday was to relax this assumption that the energy was fixed. So we're going to relax this. Let me do that in red. So we're going to relax that the energy is fixed while maintaining that the volume and number of particles is still fixed. And if we get to where I plan on being by the end of this lecture, we'll also wind up relaxing these assumptions as well, but we'll get there. First, let's deal with the energy. All right, so now as I already told you that when you do this, you keep the volume and the number of particles fixed and you relax the assumption that you have fixed constant energy, you are now working at what is referred to as the canonical ensemble. Okay, so we were essentially trying to work out some features of the canonical ensemble. All right, and the way that we did this was to define a system that is still microcanonical in nature, but allows us to look at the transfer of energy between two subsystems within this microcanonical system. All right, so we got this big box. Okay, the walls of the box are made out of unobtainium, so it does not allow the transfer of any energy into or out of the box. Okay, so fixed constant energy inside the box. And then what we did was to divide the box into two with a membrane, whatever this may, again, it's made out of some fantasy material, adamantium. So this fantasy material here does not allow the passage of any volume or particles through it. The only thing it allows is the transfer of energy across the barrier. Okay, and by doing this, we have defined two subsystems. So this is subsystem 1. And over here we got subsystem 2. Okay, and in both subsystem 1 and subsystem 2, we keep a fixed constant number of particles that is the same in both. And we just allow the energy to swish-swash back and forth between them. All right, and so the total system has an energy that we call E. And because this number is fixed, we insist that this be equal to the sum of the energies of the two subsystems, E1 and E2. And because of this, we show that that the energies of subsystem 1 and subsystem 2 are coupled to each other. That is, if I specify one of them, I have to automatically specify what the energy of the second is. So the energy of the second subsystem is always equal to the total energy of the system minus whatever the energy of the first subsystem is. Okay, so now, one of our major advances on Monday was, so what we want to calculate is probabilities. And within the microcanonical ensemble, all available states at a given energy are equally probable. Okay, and so in other words, what we're interested in doing is calculating volumes in phase space. Okay, so the volume of all valid states in phase space that is what we called omega of E, right? All right, so now one of the primary things we accomplished on Monday was to show that you can express the, well, so technically this is the density of states, not the number of states. So let's change that. So the density of all valid states in phase space is what we call omega of E. And what we showed on Monday was that you can express this density of valid states of the entire system in terms of the density of states of each of the two subsystems. All right, and so what we showed, or tried to show, was that the density of states of the total system was equal to the density of states of subsystem 1 at energy E1 times the density of states of subsystem 2, okay, at energy E2. And as we specified up here, E2, if you know E1, you automatically know what E2 is. So this is E minus E1. And then to get the density of states, what you have to do is to integrate over all possible partitionings of the energy between these two different subsystems. So in other words, you take this and then you integrate over all allowed values of E1. So in other words, from 0 to E. All right, so in other words, the total density of states is related to the product of the densities of states of subsystem 1 and the density of states of subsystem 2. Like so. All right, so that was one of the major things we did on Monday. Now, the next thing that we tried to do was to use this to answer a specific problem. Okay, and the specific problem we wanted to work was, given that this is true, what is the probability density? What is the probability density of finding density for subsystem 1 to have a specific value of the energy, to have energy that we called E1 star? Okay. All right, so now using our previous logic, this in principle is very simple, that the probability density to find subsystem 1 with energy E1 star should be equal to the volume of phase space with E1 equal to E1 star and E2 equal to E minus E1 star. Okay, so that's the volume of the phase space that has the specific set of values that we're interested in. And then we normalize this by the total phase space volume. All right, so in terms of what we just described, this would be the density of states of the entire system with E1 equals E1 star and E2 equals E minus E1 star. And this is divided by all possible states. All right, so now what we do is we want to express the numerator of this in terms of the density of states of each of our individual subsystems, okay? And so what I'm gonna do is to go back up here to this thing that we derived. And what that tells us is that this is equal to the density of states of subsystem 1 by itself, having energy E1, times the density of states of subsystem 2, having energy E2, which is equal to E minus E1, divided by...
Sorry, quick question.
Yes, please.
Is E1 and E1 star being kept intentionally separate in these two equations?
No, I'm kind of just letting them. I'm kind of being rather sloppy about it, because ultimately what's going to happen is that it doesn't matter what you call it. You're always going to get the same answer regardless of what this is. It's going to be some Gaussian that is a function of E1 star. And so regardless of the specific value of E1 star, you just plug that value into your Gaussian and that'll tell you the probability of that state. So in other words, it doesn't matter what the specific value of E1 star is, at least for this expression. And so I'm being a little sloppy about it, but that's the idea. Okay, so we're good with this now, right? Okay, so now what we can do at this stage is we can go through exactly the same kind of reasoning and math that we did to answer the similar question that we asked for the microcanonical ideal gas. Okay, so you remember back when we talked about the microcanonical ideal gas, we asked what is the probability density of finding a specific component of the momentum of one atom equal to some specific value. So we would just follow exactly the same argument and you would get more or less exactly the same answer. Okay, so what we would get if we tried to solve this problem explicitly would be that we would get that this probability density is proportional to some Gaussian. So it's going to be some function of E1 divided by some standard deviation, like so. Something like this. Okay. And in particular, as we talked about on Monday, the standard deviation is going to be related to 1 over the square root of the number of particles that we have. Okay, so in other words, the standard deviation is going to be super, 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 super small. Okay, so what we're going to get is a Gaussian, a bell curve that is centered around some mean value that is very, very narrow. So in other words, if you look at this system, what you're going to find is that, and you let the energy fluctuate back and forth between the two subsystems, eventually the system is with extremely high probability and extremely high precision, always going to settle into more or less exactly one state. That is the center of the Gaussian, and the fluctuations away from that state are going to be incredibly small. Okay, because again, the fluctuations away from that state are 1 over the square root of number of particles. Okay, so the next thing we were, before we get into that, let me draw it. So what we're going to get again is that our probability density on this axis, and we put our energy on this axis. What we're going to find is that the thing is going to have maximum probability at some specific value. And it's going to be a bell curve centered around that value. And it's more or less going to be a delta function. That is, the width of this bell curve is approximately 0. Okay, so now our question is, what is this value? What is this most likely value of E1? Okay. And so we started talking about this on Monday. So again, this bell curve is centered around, so if we zoom in on what this thing looks like, so we zoom in up here, the bell curve is centered around this most likely value, okay? And at that most likely value, that is the maximum of the probability, okay? So in other words, to find what E1 star is, we'll just take our probability density and try to determine where its derivative is 0 in order to find this maximum. Does that make sense? Okay, cool. So in other words, what we want to do is to take our probability density, and we want to, let me make sure I write it the way I want to write it. Yeah, we want to differentiate it with respect to E1 and set it equal to 0 in order to find the maximum. So this will give us the conditions in order to find the value E1 equals E1 star, where this probability density is a maximum. All right, so let's do it. Okay, so what we're going to do is differentiate with respect to E1 our expression for the probability density, rho. And our expression for the probability density is this thing right here. So let me just take this expression and substitute it right here. So it is omega 1 of E1 times omega 2 of E minus E1 divided by omega of E. Okay. All right, so what I got here, this is a function of E1. And so when I take this derivative, I have to take the derivative of this function. Similarly, this omega 2, that is also, as you can see right here, that is also a function of E1. And so when you take the derivative, you also have to worry about taking the derivative of that. This thingy down here in the denominator, though, that is just a function of the total energy. And that is a fixed constant, as you will recall. And so consequently, when we take this derivative, this total density of states in the denominator, I can just factor that through the derivative. All right, and so what I wind up with is this. Whoops, running out of space, E minus E1. Okay, so in other words, what I'm taking the derivative of a product of two functions. So you just apply your standard everyday product rule for taking derivatives. That is, you take the derivative of one, multiply by the other. Then you add on to that the other multiplied by the derivative of the second one. All right, so what we get is this. So we get, let me be super anal about this. So we get 1 over the total density of states. Okay, then we get d, whoops, omega of 1 E1, d E1. So that's just the derivative of the first function times the second function. And let me get rid of it. We don't need this anymore. So let me just write it like this. Plus the first function times the derivative of the second function. That's it. Okay? So that's how you take the derivative of this thing. And then what you do is you evaluate it at E1 equals to E1 star. And at that specific value, you insist that this thing be equal to 0, because that'll tell us where the maximum of this probability density function is. All right, so I take this thing, I set it equal to 0 in order to find the maxima. You can see that this quantity here is multiplied by the 1 over the total density of states. So in other words, I can just forget about this because it's equal to 0, and so that goes away. It's equal to 0 regardless of the value of that thing. Okay, so in other words, it's only the stuff within the brackets that I have to worry about being equal to 0. Okay, so I have this. I have omega 2 d, omega 1 dE1 evaluated at E1 equals to E1 star plus omega 1 times d omega 2 dE1 evaluated at E2 equals E minus E1 star, and this has got to be equal to 0. All right, now, the next thing I'm going to do is divide by omega 1 times omega 2. That gives me this, 1 over omega 1 times d omega 1 dE1. Okay, so that's the first term. And the second term, I get this, 1 over omega 2 times d omega 2 dE1 at E2 star equals E minus E1 star. Oh, this is starting to look pretty nice, right? So this thing right here, this first term, that is entirely expressed in terms of variables related to subsystem 1. This one is getting pretty close. This is almost in terms of the variables that describe subsystem 2. The only problem is we're taking the derivative with respect to variables describing subsystem 1. No problem, okay? And that is no problem because we again know that they are coupled together. That if we add them together, that should give us the total energy of the system, which is a constant. Okay, hence, if we take the differential of this statement, the differential of a constant is 0. So we get that. So in other words, the differential with respect to E1 is just minus the differential with respect to E2. So we can take this and plug it into here. And in doing so, we get the following. 1 over omega 1 d omega 1 dE1 evaluated at E1 equals E1 star minus, okay, we get the minus sign because when we replace dE1 with minus dE2, that gives us this minus sign here. So we get minus omega 2 d omega 2 dE2 with E2 star, whoops, E2 equals to E2 star, which is E minus E1 star. And this is equal to 0. All right, pretty nice. So again, this is entirely in terms of things that talk about subsystem 1. This expression here is entirely in terms of things that describe subsystem 2. So we have found a relationship that tells us essentially how subsystem 1 and subsystem 2 relate to one another at the maximum of this probability distribution. So now the question is, what the hell is this thing? All right, so now let me draw your attention to something that you hopefully remember from intro calculus. Okay, so let's say you have some function f of x. And then I take the logarithm of this function. And then I take the derivative of this logarithm of a function with respect to x. What does that give me? Okay, well, the chain rule says that what you do is you, first of all, differentiate the logarithm. So the derivative of logarithm just gives you 1 over the argument of the logarithm, right? So this would give you 1 over f of x times, and then the chain rule says that the next thing you have to do is take the derivative of the argument of the logarithm. So that would be df of x dx. Okay, so now look at this. And compare that to these things up here. And you'll notice that what it looks like we're doing is that there is some function that is a logarithm of the density of states. And what we're doing here is so this is some function of subsystem 1 of a logarithm. No, what am I saying? So this is some function that's equal to the logarithm of the density of states of subsystem 1. And this is some function that is a logarithm of the density of states of subsystem 2. And what we're doing, so then what this thing is, okay, so let's just do it. Let's define a function. We'll call it, what are we going to call it? We'll call it S. Why not? So define a function. Let's call this function, I don't know, let me pull it out of my rear end, S. Okay, and this function is proportional to the logarithm of the density of states of your subsystem. So for example, this S1 would be the density of states of logarithm of the density of states of subsystem 1. Now, it turns out that in order, so this function shows up in other places too. And it turns out that in order to make the units of this function turn out to be what they're supposed to be, you need to multiply this by a constant in order to make the units work out. We'll call that constant KB. Why not? Okay, so this is just a constant to make the units work out. In fact, it's Boltzmann's constant. Okay, and so by defining this function, what we're doing is that we're saying this condition to be at the maximum of our probability distribution is just that if we take the derivative of S1 with respect to E1 minus the derivative of S2 with respect to E2, and then we evaluate this at the maximum, that's equal to 0. Okay. So what is this function? Turns out it's a super important function. This is the entropy. Okay, and so this is kind of, you know, just by writing down the probability density in terms of the density of states of two subsystems that are exchanging energy with one another, and by writing down the mathematical condition to find where the maximum in that probability distribution is, just from that math falls out the definition of this quantity we call the entropy. All right, it's kind of cool. All right, so now what this tells us, by the way, this statement right here, that the entropy is equal to Boltzmann's constant times the logarithm of the density of states, this is essentially what is written on Ludwig Boltzmann's tombstone, because it's that important. And if you wind up getting something like this written on your tombstone, then you're doing pretty good for yourself. All right, so the entropy is just some constant times the logarithm of the density of states. Okay, so what we get with this definition of the entropy is this statement right here, that the derivative of the entropy of subsystem 1 with respect to the energy of subsystem 1 is equal to or minus the derivative of the entropy of subsystem 2 with respect to energy 2 is equal to 0. Another way to put this, if we go back to putting the derivative of the second entropy in terms of energy 1, so if we go back to writing this like this, okay, we get this condition. In other words, the most likely value of E1 occurs when the total entropy S1 plus S2 is a maximum. Okay, so you take these two systems, you let them exchange energy with one another, so the total energy of these two systems can fluctuate. And what they're going to do is eventually settle down to some equilibrium value of the energy in subsystem 1 and subsystem 2. And what this analysis shows is that that most likely arrangement of E1 and E2 occurs where the entropy of the total system is a maximum. Okay, so that's so important, let's write it out. So the condition that a maximum occurs in our probability density is that the total entropy S1 plus S2 is maximized. Okay, so at the most likely value of E1, the entropy of the system is a maximum. Okay, does that make sense to everybody? And it turns out, so in your syllabus, one of the like extra textbooks I suggested you have a look at this Thermodynamics and Thermostatistics by Herbert Callan. This is the best thermodynamics book I've ever read. So what he does, like on page 1 of this book, what he does is just assume that there must be a quantity that you call entropy. And by showing or by assuming that you're looking for the maximum values of this quantity called the entropy, you can derive the entirety of thermodynamics. It's amazing. And it's also the only book I've ever read that actually makes thermodynamics make any sense to me. Okay, so the entropy is a fundamental function in all of physics. It's like as fundamental and as important as something like energy. So entropy is extremely important. Okay. All right, so now let's find out where this maximum is. Okay, so our condition for E1 star is this, that the ds1 dE1 evaluated at E1 equals E1 star has to be equal to ds2 dE2 at E2, whoops. Okay, so this is, we got that from right here, right? So all I'm doing now is just moving the entropy of the second subsystem over to the right-hand side, and you get this. Okay, so now, has everybody taken thermodynamics? It's like a requirement to take this class, right? So you've all taken thermodynamics, yes?
Yeah.
Coca-Cola. Okay, very good. All right, so now in thermodynamics, you've also run into the entropy before, hopefully. And in thermodynamics, you can show that what you define as the temperature, so the definition of temperature from thermodynamics is this. It is 1 over the temperature is defined to be the derivative of the entropy with respect to the energy at constant volume and number of particles. Oh, that's what we're doing here. We have a constant, let's go back up here. We have a fixed constant number of particles. So all these derivatives that we're taking are with a fixed constant number of particles. And so the derivative of the entropy with respect to energy with a fixed constant volume and number of particles is 1 over the temperature. Okay, so you compare this definition from thermodynamics to this condition that we just got for the most likely equilibrium value of E1 and E2. What you see is that this occurs when T1 equals T2. So in other words, the most likely value of E1 occurs when the entropy of the total system is maximized. And because of the relationship between entropy and temperature, that state is when the temperatures of the two subsystems are equal. So the equilibrium, so you put these two subsystems next to one another. Say one's really hot, that is, it has a high temperature, and the other one is really cold, that is, it has a low temperature. They're going to start swapping energy back and forth between them. And the state that they eventually settle into in equilibrium is that where the two temperatures are equal. Okay, so this is just a big fancy way of showing what you already learned before in thermodynamics, that the equilibrium of the system is when the temperatures of your two subsystems in contact are the same. Okay, so cool, right? Cool. All right, so now in the remaining 10 or so minutes, all right, so what we did was we started out in the microcanonical ensemble where we had fixed energy, fixed volume, and fixed number of particles. And what we did was we relaxed this and allowed the energy to fluctuate, but we maintained constant volume and number of particles. And again, when you do this, so this is the microcanonical ensemble. When you relax the constraint that the energy remains constant, this becomes what you refer to as the canonical ensemble. And you can maybe guess what the next thing we're going to do is. We are going to relax these constraints. We are going to allow the volume of the box to change and allow the number of particles to change. And when you allow this to happen, this is what's referred to as the grand canonical ensemble. Woo. Okay. So first of all, let's describe how we're going to do this. So again, we go back to our microcanonical box. So here is our microcanonical box that is sealed from the outside world. No energy can get in or out. Now, what we did to look at how the canonical ensemble would behave from this is we put a barrier down the middle that allows energy to flow back and forth. And so now what we're going to do is to put a barrier down the middle that, first of all, so part of it is going to allow energy to flow back and forth as we did previously. The next part is going to be like a rubber membrane. So it's going to be something made out of rubber such that it can bend back and forth. So it's going to be something that can bend like so. Okay, and as this thing bends, you can see that what's happening is that you're changing the relative volumes of subsystem 1 and subsystem 2. Okay, so across this upper membrane, we allow energy to move back and forth. With this membrane, we allow volume to change. And then what we can do is also put in a thing, essentially a porous part of the membrane that, say, looks like this. That allows particles to travel back and forth between the two subsystems. So we also allow the two subsystems to exchange particles. Okay, does that make sense? All right, so now our guiding star when we went from microcanonical to canonical was the fact that the total energy had to add up, or the energy of subsystem 1 plus the energy of subsystem 2 had to add up to the total fixed energy of the total system. So now with this, we're going to have similar constraints on the volume and the number of particles. So the total volume of the system also has to add up to V1 plus V2. And the total number of particles has to add up to N1 plus N2. Okay. And so what this tells us, again, just like when we were discussing the canonical ensemble, that if you specify the value of the energy for one of the subsystems, you automatically know what the value is for the second one. Same deal with these quantities. Okay, so here, if we specify what E1 is, we automatically know what E2 is, because that's got to be true. If we specify what V1 is, we automatically know what V2 is, because that's got to be true. And if we specify what N1 is, we know what N2 has got to be, because that's got to be true. Okay, and now also, what we just did a couple minutes ago is we take the differential of this statement. And the differential of this tells us that dE2 has to equal minus dE1. So that just tells you that if I increase the amount of energy in subsystem 1, that increase had to come from a decrease in subsystem 2. Okay, so similarly, if you're looking at volumes, if the volume of subsystem 1 goes up, that means the volume of subsystem 2's got to go down. Okay, so in other words, dV2 is equal to minus dV1. And same for the number of particles. Okay, I'm going to need that. Okay, so now, what we're interested in are the values of the energy, the volume, and the number of particles in each of the subsystems at the equilibrium value. That is the most likely value. And as we showed when working in the canonical ensemble, that most likely value occurs at a maximum in the entropy. And so we're going to make the same assumption here. Okay, so when we worked in the canonical ensemble, we assumed that the entropy was just a function of the energy. And with everything else fixed. In the grand canonical ensemble, we assume that the entropy is a function of all of these things. It's a function of the energy, the volume, and the number of particles. Okay, and so now what we want to do is to take the total entropy of the system. We want to differentiate it and force it to be a maximum. So in other words, we're gonna do this. Okay. All right. So now what we're gonna do is differentiate a function of 3 different variables. So now hopefully you've taken calculus 3 and you know how to write down the differential of a function of multiple variables. It is this. So ds is equal to ds dE1 at constant volume and number of particles plus ds dE1. Let's see, what am I trying to do here? No, let me write it like this. dE2, there we go. That fixed V and N times dE. Okay, so what I'm doing here is I'm allowing the energy to vary while keeping the number of particles and volume constant, and I get this sum of differentials. And then I hold the energy constant, the energy and the number of particles constant, and I allow the volume to vary, and I get this. So this is a constant energy and number of particles. Whoops, I'm sorry. This should be a minus sign right here, and this should be a minus sign. So I get that when I allow the volume to vary. And again, this minus sign here and here, where that's coming from are these relationships right here. Okay. And then I hold the energy and the volume constant, and I get a set of these with respect, variations with respect to the particle number. Okay, so that's the differential of S. So this is just pure math here. I mean, you have a function of several variables and you write down the differential of it. This is it. And then we take this differential and we insist that this be equal to 0 in order to find the maxima of this function. Okay, so now each of these variables, energy, volume, and number of particles. So you can kind of think of these, so these are independent variables, and you can kind of think of these as something like unit vectors. Okay, so for a vector to equal 0, each of the coefficients of each of the unit vectors has to be equal to 0. Same deal with this, because these are independent variables. In order for this whole thing to be equal to 0, each of these, this differential has to equal 0, this has to equal 0, and the third one has to equal 0. Otherwise, it can't equal 0. Okay, so now our next job is to figure out what each one of these things is telling us. So first of all, let's look at this first one where we allow the energy to vary. So when we allow the energy to vary, what we get is that ds dE1 minus ds dE2 Vn is equal to 0. Well, that's exactly the same, Dan. That's just exactly what we spent the past hour doing, right? So when we just allowed the energy to vary and keeping everything else constant, this is exactly what we got. And again, from our definitions from thermodynamics, what this told us was that the two temperatures are equal. So now the next question is, what do these other two things give? So what does this tell us? And what does this tell us? And that is what we will do on Friday. Although before we go, just as from thermodynamics, we had this relationship that the temperature was related to this derivative, we have some other relationships from thermodynamics that we need to keep in mind. So we'll need to remember, and if you don't remember, you should go look this up just to refresh your memory, that you can also define the pressure. The pressure is the negative derivative of the energy with respect to volume. So this is, remember, from thermo. And something called the chemical potential. So this is the pressure. This is the chemical potential. And we'll talk, if you're not too comfortable with chemical potential, we'll talk about more what this thing is. And what this is the derivative of energy with respect to particle number. Okay, and so what we're going to do on Friday is to take these results from thermodynamics and plug them into this thing up here to tell us what these conditions are at equilibrium that StatMech is telling us. All right, sound good? Does anybody have any questions? Outstanding. All right, so next time we meet will be the discussion section at noon on Friday, if you so choose to join us. If you don't, then it'll be the lecture at 4 on Friday. So until then, oh, wow, communication by emoji. Fantastic. All right, I'll see you guys then.